So, a very good afternoon to all of you. Now, in the lecture series of chemical measure trace and ultra trace analysis, this will be the fourth lecture. So, again, to repeat, my email address and mobile number is given here, but I have yet to receive any mail from all of you. I hope you are going through the lectures. So these are the, like we have covered this in first lecture, then this one in second lecture. Now this also has been covered in third lecture, and in today's lecture we are going to cover this, the electroanalytical techniques and thermal analysis. So this lecture, the content of this lecture will be basics of electrochemistry, voltammetry and its application in inorganic and organic analysis, thermal analysis, its basic, then TGA, DTA with applications, and DSC with application, then thermometric titrations. So now to start with, let us see the electrochemistry. Now electrochemistry actually is the study of transfer of electrons. So there's production of electricity from energy released during spontaneous chemical reaction is one side, and the other side you are generating chemical energy by application of electrical energy. So these two are two different aspects of electrochemistry. Now, like when we talk about electrochemistry, immediately to our mind comes is the electrochemical cell. So what is the electrochemical cell? Now it is either like galvanic cell or Daniel cell, which is a spontaneous reaction. So like if you have these two systems, copper and zinc, then copper will be reduced and zinc will be oxidized is the spontaneous system. So this is the reaction, and this comes under the galvanic cell. So the copper 2 plus zinc giving copper and zinc 2 plus. So finally here zinc is getting oxidized and copper is getting reduced. Oxidation. So the total E cell you can calculate. Now electrolytic cell, what is electrolytic cell? Here it consumes electrical current and produce chemical energy. So it is non-spontaneous reactions are made to happen by consumption of electrical energy. The same reaction, if in the forward direction, in this direction it is spontaneous, then obviously in the backward direction it will be non-spontaneous. So that same reaction here can be made using an electrolytic cell, and where the E cell will be again minus. The exactly equal these values are, only the convention in sign. Here it is positive and here it is negative. So now the various terms, whatever been used in a electrochemical cell or galvanic cell or Daniel cell is the anode, cathode, salt bridge and electron flow. So what is the anode? Anode is the electrode where oxidation occurs, and cathode is the electrode where reduction occurs. So you have to remember this. Anode means oxidation and cathode means reduction. Now there is a salt bridge, which is a device used to maintain the electrical neutrality of two solutions. This will get clear in my next slide. So this is a salt bridge to maintain the electrical neutrality. And electron flow is always from anode to cathode, and through the wire. It will be from anode to cathode, because anode where oxidation is occurring, removal of electron means it is electron rich. So from there it will be transported to cathode, where those electrons will be accepted by the metal ion and it will get reduced. So reduction is occur at there. So now cathode of an electrochemical cell, the electrode at which reduction occurs means you can see there 3 examples are given. Copper 2 electron copper, silver 1 electron silver, and zinc 2 plus 2 electron zinc. Now see the difference in electron transport. For copper and zinc, 2 electrons are getting transported, whereas for silver it is 1 electron. And anode is a electrode where the electrochemical cell is the where oxidation occurs. So it is copper 2 plus, or hydrogen. So it will be hydrogen ions. Now this is the pictorial diagram, a Daniel cell, where you can look at, this is a zinc electrode where oxidation is happening, like zinc is getting zinc 2 plus, And now when zinc is becoming zinc 2 plus, you can imagine in the zinc sulfate solution, zinc ion are getting increased. So for electrical neutrality, the sulfate ion will come from the salt bridge. This salt bridge contains Na2SO4, where the ions can transport easily from one cell to the other, from one beaker to the other beaker. And this is the copper cathode, which is positively charged, where it is the cathode, and this reaction is happening at the cathode. The reduction is happening at the cathode, and at the same time, since copper ion are getting consumed by getting deposited in the electrode, so the sulfate ion are becoming extra here. So this sulfate ion will then move towards through the salt bridge to this solution. So this thereby the electrical neutrality is maintained, and because of this electrons are getting flow, so current will be flowing from this side. So this is a voltmeter to so that current is flowing like this. Okay, so this is what is that. Now say electrolytic cell, that was the galvanic cell or Daniel cell. Now it is electrolytic cell, where we need to apply electrical energy so that the reaction will happen. Now you can see the formation of sodium metal. Like sodium metal, where industry in the industry it is formed by electrolysis of molten sodium chloride. Why molten sodium chloride? Because anyway, you know, aqueous sodium chloride electrolysis, hydrogen and oxygen will be getting evolved rather than sodium and chloride. So it is molten sodium chloride. So it is a non-spontaneous reaction converted to spontaneous reaction by application of external energy, electrical energy converted into chemical energy. So now you can see this is the half cell reactions and a 2Na. So this sodium metal at the cathode is getting deposited, and chlorine gas at the anode is getting evolved. So the overall reaction is 2NaCl, 2Na plus Cl2. So the molten sodium chloride, now it is forming sodium metal and chlorine gas. So this is the industrial process of formation of sodium metal. So now the standard cell notation. Normally, at all time you cannot make the whole system. So there is a notation. From the notation, you can find out which is the anode, which is the cathode, and how it has been arranged. So the convention is that anode is on the left side. Single line represents the phase boundaries like zinc, zinc plus. So that means zinc electrode is in contact with zinc solution. So that is the single line. And again, there is the double line. Double line represents the liquid junction. And this is actually, in this case, this is the double line shows the salt bridge. Because now here is a one interface of solid to liquid, and there is another interface of solid to liquid. So one interface of solid to liquid, a single line. So in salt bridge, there are two solid to liquid interface. Therefore, double line. So this is the salt bridge. So this is how the notation goes on. Now, as you know, you must be knowing that all the electrochemical cell or all the calculation are based on the Nernst equation. So in electrochemistry, the Nernst equation is an equation that relates the reduction potential of an electrochemical reaction, that is half cell or full cell reaction, to the standard electrode potential, temperature and activity, often approximated by concentration. Activity is normally taken as concentration, though we write everywhere like activity, but it is the concentration, because for dilute solutions activity equals to concentration of the chemical species undergoing reduction and oxidation. So now that what is a standard electrode potential means, this is the electrode potential where all the concentration is in molar, like 1 molar, and it is well defined, like in standard conditions the electrode potential is standard electron potential. So it was named after Walter Nernst, a German physicist chemist who formulated the equation. So now a quantitative relationship between cell potential and concentration of the ions is given here. You can see E is the electrode potential, is the E0 is the standard electrode potential, equal to 2.303 RT by NF log the reduced species by oxidized species. So this is what, and you know, then R is the gas constant, F is the number of Faraday, and T is the temperature, room temperature. So 298 degree Kelvin, always actually temperature is represented in Kelvin rather than degree centigrade. So this is the final equation is this. So this is a constant taking into account R, F and T. Now this is the final Nernst equation for a cell. Now standard thermodynamics says that the actual Gibbs free energy delta G is related to the free energy change on the standard state delta 0 by the relationship delta G equal to delta 0 R tilde QR, where QR is the reaction quotient and R is the again the universal gas constant. So these are the equations. Now, what is electroanalysis? With this basics of electrochemistry, now electrochemistry is used for analytical purpose. How? Now you can measure the variations of an electrical parameter, because all these are measurable quantities. So you can measure either the potential, current, charge, conductivity, and relate this to a chemical parameter, that is the analyte concentration in case of analytical chemistry. So like that, you can use electrochemistry as an analytical method. So now you can, based on these measurements, either you can do a conductivity, potentiometry. Like potentiometry measurement, you may be the widely used pH electrodes or ion selective electrodes. ISE is nothing but ion selective electrodes. So now coulometry, which is the actually electrogravimetry, deposition of metals, and then voltammetry. These are the very important methods. Now we'll be in this lecture, we'll be concentrating only on the voltammetry, because this is where we are going to use the trace and ultra trace analysis. All other methods are not for trace and ultra trace analysis. They can be used for percentage level or milligram level analytes, but voltammetry we can use for trace and ultra trace analysis. And therefore, in this lecture, we'll be concentrating on voltammetry. Now, what is voltammetry? Voltammetry is the measurement of current as a function of voltage under non-equilibrium conditions. Uses a polarized macroelectrode for measurement. The scanning of voltage allows more than one analyte to be determined at once. Can be used for both aqueous and non-aqueous solutions. And this voltammetry, when the working electrode is a mercury, then the specific technique is known as polarography. So you can see the design of a cell in case of voltammetry. So these are the three electrodes will be used: reference, working, and counter electrode. And then this is the electrolytic solution. There is a cap here, and these are the electrical. All these three electrodes will be connected to some electrical connections to make the instrument. So let us see it in some details. Now, although the electrochemical cell needs only 2 electrodes to operate, as till now we have seen in the Daniell cell or galvanic cell that there are 2 electrodes, but it is very beneficial to introduce a third electrode. This third electrode is a reference electrode, that is an electrode which has a known and fixed electrode potential. You may be knowing the reference electrodes are like calomel electrode is a reference electrode, standard hydrogen electrode is a reference electrode, AgCl electrode is a reference electrode. For all these electrodes, the potential is a known quantity. So therefore, it is used, and all the measurement of potential are done with reference to this. Therefore, because it is an analytical purpose, you are using this for analytical purpose, so there should not be any error in measurement. Therefore, you are keeping a reference electrode so that potential can be correctly measured. So no current should ever pass this electrode, as a current would change its potential and possibly damage this electrode. So the reference electrode is only for referencing purpose. The reference electrode is used to control the potential of the working electrode by measuring the voltage between these 2 electrodes. Now, there are 3 types of electrode, as you have seen in the previous picture. One is working electrode, which makes contact with the analyte and allow charge transfer with the analyte, and that is the main electrode where all the oxidation reduction reactions will be happening, and therefore by that we will be analyzing our analyte. Now, reference electrode has a known reduction potential and it does not pass current. It measures and controls the potential of the working electrodes only. The most common reference electrode for aqueous solutions are the calomel electrode and the silver chloride electrode. You must be aware of this type of reference electrodes. Now, auxiliary electrodes or counter electrodes. What is this? It connects the working electrode to the electrolytic solution. It ensures that all current generated by the working electrode flows through the cell without passing through the reference electrode. So that is where there is an auxiliary electrode. Now, depending on this, there are various types of voltammetry. So these methods are evolved with a time period depending on the requirement. So now let us see the major type of voltammetric techniques. here. So voltammetry is an electrochemical technique where the current is measured. What is voltammetry? Here we are measuring the current as a function of applied potential. So we are going to apply the potential, and at the same time, what is the change of in current? So you will be measuring the current. So this helps to study redox reactions and determine the analyte concentration. The different voltammetric methods provide specific information based on the experimental setup. So the first one is linear sweep voltammetry. This is the primitive type and the first one during the evaluation of voltammetry. So the linear sweep voltammetry. So what is the principle here? The potential is linearly increased. Potential is linearly increased over time, and the resulting current is measured. Now the analyte undergoes oxidation or reduction when its redox potential reached, and this generates a peak in current. So when the reduction potential of the analyte reaches during the sweep of the potentials or slow increase in the potential, then suddenly the analyte will start doing its redox reaction, and so the current will increase. So application is metal ion analysis and studying electrochemical reaction mechanisms. The example are determination of ascorbic acid content by monitoring its oxidation peak during the scan. So you can see that the linear sweep means slowly with time, the potential is increased slowly. So this is the potential and time, it is, and corresponding current is being measured. So this is the type of curve you will be obtained during this linear sweep voltammetry for some metal ion. The relationship between the concentration of the analyte and the limiting current is given by the Ilkovic equation. Ilkovic equation is a very famous equation for electrochemistry. So this is the expression is written here. Here you can see the terms where n is the number of electrons transferred in the redox reaction. As you have seen, for copper it is 2, for silver it is 1, and like that. So you must be knowing whatever system you are, like what you are analyzing, you have that idea, and so you can know the number of electron transferred in the redox reaction. D is the analyte's diffusion coefficient. M is the flow rate of the mercury. Now it is all with mercury electrode, so it is the flow rate of mercury. And T is the drop time. The half wave potential E half provides qualitative information about the redox reaction. Now cyclic voltammetry. What is cyclic voltammetry? The potential is swept to forward and then reverse, forming a cyclic potential. The resulting current is plotted against potential, and redox reactions occur during the forward and reverse sweeps, creating a characteristic cyclic voltammogram. So that both of the pictures is given in the next slide. So application is to study the redox reaction, reaction kinetics, and electrochemical stability, like analyzing electron transfer in metal complexes, or redox active drug is an example where you can utilize cyclic voltammetry. So you can see here in cyclic voltammetry, normally we complete a scan in both the direction. Figure below shows a typical potential excitation signal. In this example, we first scan the potential to more positive value. See, first this one and then this one. So you can see here it is scanned in the more positive value, resulting in the following oxidation reaction. So when it is more positive towards more positive, then the reaction R will be getting oxidized to O. And then when the potential reaches a predetermined switching potential, because you have to first predetermine from where you are going to switch the opposite direction scan. So you have to predetermine that. We reverse the direction of the scan when it reaches the predetermined value towards more negative potential, and because we generate the species O on the forward direction, during the reverse scan it will again reduce back to R. So now you can see for this we will be getting this type of peak. So the peak current in cyclic voltammetry is given by Randall-Sevcik equation. It is given here. And where the N is the number of electron in the redox reaction, A is the area of the working electrode, D is the diffusion coefficient for the electrode species, and mu is the scan rate. Now since you are scanning at a particular rate, so mu, and depending on the scan rate, your cyclic voltammogram will be of different shape, from which you can bring out various informations and see the concentration of the electroactive species at the electrode. The third one is the differential pulse voltammetry, or DPV. So this is the superimposed small voltage pulses onto a steadily increasing potential, measuring the current difference between before and after pulse. So the differential measurement enhances sensitivity by reducing background current. Trace level detection in pharmaceuticals and environmental samples can be done by this, and determination of trace metals like lead, cadmium in water samples also can be done by this type of voltammetry. What is square wave voltammetry? It applies a square wave potential on the top of a staircase potential, measuring the net current at the end of each pulse. Now, how it works is that it increases sensitivity by reducing background current and enhancing the signal response. All this picture and all you will be getting in the standard book, whatever which I have given in my first class. So this is standard book of David, and in that you can get all these type pictures of all these things. Now, application for this is fast and sensitive detection in biological and chemical analysis. Detection of dopamine in biological fluid can be done by this. Chronoamperometry. Now, as the name suggests, here a fixed potential is applied and the resulting current is monitored over time. So, chrono means chronological order with time, amperometry means current. So, now in this case, a fixed potential is applied and the resulting current is monitored over time. The analyte reacts at the electrode surface, generating a time-dependent current, and this can be applied to determination of diffusion coefficient and reaction kinetics, analyzing the diffusion control, reduction of oxygen in water. So these are the examples. Now, chronopotentiometry, again, here it is a fixed current is applied and the potential is monitored over time. So the applied current causes a time-dependent change in potential based on the analyte's concentration. So the analysis of electroactive species in battery and corrosion studies, investigating corrosion potential in steel samples, all those are the applications. Anodic stripping voltammetry. So analytes are pre-concentrated on the electrode surface and then stripped off by reversing the potential, generating a sharp current peak. So we will be seeing few examples based on this technique ahead. Now, how it works? The analyte's oxidation or reduction potential generates during current signal upon striping. Now, first of all these metal ions will be deposited on the mercury drop, and then they will be stripped back again. So trace metal detection in environmental samples, measuring trace lead, mercury and arsenic in drinking water is one type of example. Then similarly, there is a cathodic stripping voltammetry where the analyte is deposited onto the electrode surface again, followed by reduction, generating a current peak. A negative potential removes the deposited analyte, generating a peak in the current. In the previous case, it is the positive potential. Here it is a negative potential which strip back. Now, the detection of halides in organic contaminants, determination of chloride concentration in water samples are the example. So, cathodic stripping voltammetry is for chlorine, whereas anodic stripping voltammetry is for metal ions. So, this you have to see. Now, the normal pulse voltammetry, it is a series of increasing voltage pulses is applied and the current is measured at the end of each pulse, suitable for studying fast electron transfer processes, and determination of pesticides in food samples are one of the example. So now what is the conclusion when you look all these things is that voltammetric technique provides versatile and powerful tools. As you have seen from the examples, it is widely used starting from the metal ion detection to biology to detection of organic molecules and everything. So now the voltammetric technique provides versatile and powerful tools for electrochemical analysis, enabling sensitive detection, reaction studies, and trace level quantification across diverse scientific and industrial applications. So the choice of technique depends on the analyte's electrochemical properties and the required level of sensitivity and precision. So as in the first class we have seen, there are like various parameters based on which you will be choosing one technique. Like what is the sensitivity you require, what up to what level you have to detect and all. So depending on that, again, electrochemistry, you can choose one method. Now let us focus something into polarography, which is using a mercury electrode, because that is the most common one. So consider the reduction of a metal ion at the mercury electrode. Then what will happen? The metal ion, when it is getting reduced, it will form some amalgam of the metal at mercury. So at the voltage is swept, the current will remain constant since the microelectrode is polarized. until the voltage is sufficient to drive the above reaction. Now the current will then increase to reach another limiting value. So this type of curve you will be getting in a case of a polarography. So what is the, here you can see many terms: residual current, limiting current, and this is the diffusion current. Which is the diffusion current? This one is the diffusion current. This diffusion current is limiting minus residual current. So now what is residual current and where it is it comes? It is because residual current is in polarography refers to the small non-Faradic current that flows through the electrochemical cell even in the absence of the analyte being reduced or oxidized. So it is the combination of capacitive current and limiting current from impurities in the electrolytic solution, but not from the analyte. Okay. So now all the polarographic calculations are based on Ilkovic equation. You must have heard this term, Ilkovic equation. It is a relation used in polarography relating the diffusion current ID and the concentration of the depolarizer. That means depolarizer is analyte, which is getting depolarized, which is the substance reduced or oxidized at the dropping mercury electrode. And the Ilkovic equation has the form of this, where K is a constant which includes Faraday constant and has been evaluated as 708 for maximum current and 607 for average current. Now what is this maximum and average current? It will come ahead. Now D is the diffusion coefficient of the depolarizer in the medium. N is the number of electrons exchanged in the electrode reaction. M is the mass flow rate of mercury through the capillary, that is milligram per second, mass flow rate, so milligram per second, and T is the drop lifetime in second, and C is the depolarizer concentration in millimole, which you want to determine. Now you can see here some, there is another important thing, the ID at 2. Here this is the diffusion current and this is the half-wave potential. It is known as the half-wave potential. Half-wave potential is a potential at which polarographic wave current is equal to 1/2 of the diffusion current. In a given supporting electrolyte, the half-wave potential is unique for each element and its different valence states and chemical form. So half-wave potential will be different for different species, as well as it will be different for different oxidized species for the same analyte. Say arsenic 3 and arsenic 5 both have different half-wave potentials. And it is not that arsenic, since this is the element, so 3 and 5 will have the same half-wave potential. No. So like it depends on element to element and also the different oxidation species or different species of the element. So observation of a current peak at a specific half-wave potential therefore identifies the chemical species producing the current. So unlike in case of like atomic absorption spectrometry or ICP-OES, where you are always determining the total concentration of the analyte, here in case of electrochemistry there is a possibility that you can find out the species, whether in the sample arsenic 3 is present or arsenic 5 is present, because you must be aware that between arsenic 3 and arsenic 5, arsenic 3 is more toxic. So now if you want to know how much is the arsenic 3 and how much is the arsenic 5, you will not be able to do that with spectrophotometry or atomic absorption spectrometer. But yes, in case of electrochemistry, that can be done. So now if two metals are present, because it is a multi-element technique, if two metals are present, then you will get two curves like this. So there will be two diffusion current, ID1, and this will be ID2, and again two half-wave potential connecting to two different species. So this is what you should remember, when there are 2 or 3 elements, then if 3, then another peak will be getting here. So if two metal ions are present, a second wave could occur, and the height, diffusion current of the wave relates to its concentration. The arrow indicates the half-wave potential, which is the voltage at half the diffusion current, and relates to the type of the analyte. So now you can see there are different types of mercury drop electrodes for the polarography to happen. What's the hanging mercury drop electrode? So you can see this is the hanging mercury drop electrode, means this is the drop is fixed for throughout the process. So this will be hanged inside your solution. Dropping mercury electrode, where there are the mercury drop will form, slowly its size will increase and then it will drop. Again a second drop will form, its size will increase and drop. So what happens is, at every time you are getting a new surface for reaction. And then in case of SDME, the static mercury drop electrode, so the measurement is happened like here also the same like dropping mercury electrode, but the measurement of current is only at the stable size of the drop. So when the drop is forming, then it is attaining a particular size. At that time, the current will be measured, and then it will be there will be a mechanical impact to the electrode, and the drop will fall. Then again a drop will form. Then when it attains a particular size, then the measurement will happen, and again it will fall by some physical impact. So that's the static mercury drop electrodes. All these three electrodes have different applications, and you can use depending on your analytical problem. So energy stripping voltammetry, now let us see what is the energy stripping voltammetry. So consider the analysis of a mixture zinc, cadmium and copper. Now zinc has this potential of reduction potential, cadmium is this, and copper with this potential of reduction potential. So now how it does is that firstly bubble nitrogen to displace oxygen to avoid its interference. So there will be a reaction cell where your sample will be taken, where you want to analyze the zinc, cadmium and copper. Now first you need to bubble nitrogen through the solution to expel all the oxygen, because you know whenever there is a sample is there, so there will be present some dissolved oxygen, and oxygen can interfere in your analysis because it is a very good redox element. So you have to bubble nitrogen so that oxygen will be expelled. Now apply voltage of around minus 1.2 volt, because the maximum is minus 1 volt. So you have to apply minus 1.2 volt when all zinc, cadmium and copper will get deposited at the mercury drop. So because you see the reduction potential of these three elements are minus 1, minus 6 and minus 2. So now you are applying minus 1.2 volt. So where all these elements will get deposited in your mercury drop. Now during this you have to stir the solution during this deposition, because you want to a better mixing in the solution, and all the like analyte, the zinc, cadmium and copper whatever are present in the solution, they should approach the mercury drop, because it is a very minute drop, and if solution is around 10 ml or 25 ml, so they all should reach there effectively. So you have to stir it. Now you have to stop tearing, like the time of deposition you have to decide, and it all depends on the concentration of the elements. If they are very less, like in ppb level, then you have to take long time for deposition, so that effective concentration can deposited in the small mercury drop, and then you have to scan it, they have to strip it. So stop the stirring and the scan the voltage from now minus 1.2 to 0, so that all these things will come one by one. So pictorially it has been represented in the next slide. So you can show now you have deposited minus 1.2 potential is applied, and it is getting deposited, and now you are striping it from minus 1.2 to 0. So now during the striping, you see first zinc will come, then cadmium, then copper. So this type of peaks you will be getting for all the three elements. Okay. So the deposition time can be varied, or longer time for a lower concentration. The deposition voltage is selected to ensure all analytes can be deposited at the hanging mercury drop electrode. And the use of stripping allows concentration at ppb levels, but should not be used for high concentration. If you are using this technique for very high concentration, then the mercury drop, it is a micro drop, very small drop. So now all your metal ion will go and deposit there. So if the metal ions or your analytes are in ppm range, then what will happen? No, this will saturate. So if once it is saturated, then there will not be a uniform deposition of all these analyte onto the drop. So therefore, you should not use this technique for ppm range. Now note that in the stripping stage, the direction of the reaction is reverse. That is zinc, cadmium and copper ion. In the deposition, it is the reverse, and striping, it is the reverse. And that is expected also, because their potential are in that order. So zinc, cadmium, copper ions released into the aqueous phase in the example. So the reaction must be reversible. Now to follow this method of analytical method, whatever the metal ion or for which you are doing that should be a reversible. Like when you are applying minus 1.24 2 volt, all these metal ions are going to deposit on the mercury drop. Now, once you are reversing the potential for stripping back, they should come to the solution. It should not be like that they have formed a permanent amalgam with mercury, and while stripping back, they are not coming out of that. So for those type of things, it will not work. So the reaction must be a reversible one. So this is now the measurement of one example for this is the measurement of uranium in ppb level. So for uranium now, to make its deposition potential in the amenable region, it has been complexed with chloroanilic acid. So this is the structure of chloroanilic acid. So ultra trace concentration of uranium-6 have been determined using adaptive stripping voltammetry of the uranium chloroanilic acid complex. Now 3 electrode reaction system. It is the reference electrode here is the silver chloride electrode, auxiliary electrode is platinum, and working electrode is hanging drop mercury electrode. Now adjusted stripping measurements were carried out in the differential pulse mode using a pulse amplitude of minus 50 millivolt, a pulse time of 30 millisecond, and a potential step of 4 millivolt. Now all these parameters, if it is a new system, you have to optimize all these parameters by doing hit and trial, and in which case you are getting a best result. So these are being optimized. Detection limit with this method is you can approach up to 10 nanogram per liter or like 100 nanogram per liter. Nanogram per liter means it is, you can see it is going in the PPT range. So this is a instrument in our lab, so Metro Moto Lab 30, which is being used for this type of work. So these are the various, like this is a good publication. So this is the various parameters that have been used for this analysis. Now you can calibrate the instrument by taking various standards because certified reference materials are available from Merck or any other source. You have to use that to standard to make a calibration curve. Here you can see now calibration curve of like 0.1 to 1 ppb. This one, and then 2 to 8 ppb, this one. This is the calibration curve for the system, and then you have to use that for calculating your concentration in the sample. So now what are the advantages of this voltammetric technique? So like quantitative determination of inorganic and organic species like ions and molecules, they are best suited for species which can be either oxidized or reduced on electrodes. A species which is not electroactive cannot be done by this method. Now it is better suited to determine inorganic species than organic compound, because what is the reason? Because in the analysis of organic compounds only very rarely a single compound is present, and in case of mixture of organic compounds we need combinations with separation techniques, because without separating now we don't have an idea of all those oxidation reduction potential of these molecules, and actually what are the organic components present in the sample also we don't have an idea. So for that it is very difficult for a mixture of organic compounds. You have to use first a separation techniques to separate all the organic components. Now for the determination of inorganic species in aqueous solutions, organic compounds present in the sample have to be completely destroyed, otherwise they will interfere. Now therefore the sample digestion by hydrogen peroxide or UV radiation is required. You know UV also decomposes organic components. So first, if you are going to do any inorganic components in your sample, you need to decompose all the organic components, otherwise you will not get a correct result. It probes the species really existing in solution, which is not the case for atomic spectroscopy, as I have just told in my previous slides. In case of atomic absorption spectroscopy or any ICP-OES and all, you are calculating the total amount of a species, say arsenic or say antimony. For antimony, you are calculating the total antimony concentration in a sample. But however, if you are doing it properly, then electrochemistry can provide you information about antimony 3 and antimony 5. So the speciation is possible. It is primarily used to analyze solutions. Applications to solid samples are possible, but this requires much more sophisticated strategies, and it is not very routine to use solid samples by this technique. The instrumentation is rather inexpensive when compared to atomic spectroscopic technique, and also it is very small and lightweight so that it can be taken to field for field use. So these are the various advantages of these voltammetric techniques. Now let us look into the thermal analysis. Now what is, so all these are the electrochemical techniques. In that I have not covered details of conductometry, coulometry and potentiometry, because all those techniques does not give you information regarding trace and ultra trace analysis, of which the lecture is all about. So only voltammetry is the technique which can go to such levels, and cyclic voltammetry also, which can give you information regarding the oxidation and reduction behavior of your analyte. So therefore that has been covered. But yes, whatever book information I have given in my first class in the last slide is there. Electrochemistry also is present there, explaining all these techniques very well. So now thermal analysis. So what is thermal analysis? Thermal analysis refers to a group of techniques used to study the physical and chemical properties of materials as a function of temperature, and therefore the name thermal analysis, because the properties are being studied with reference to temperature or time under controlled condition. Now these techniques measure changes in properties such as mass, heat flow, because if you heat a sample, then what will happen? Its mass will change, either it can oxidize or reduce, or moisture can go. So there is a change in mass. Now heat flow, depending on its heat capacity, so its dimension, mechanical behavior when a material is subjected to heating, cooling or isothermal conditions. So all these changes are being monitored and probed for all the various thermal analytical techniques. So the most common thermal analysis techniques are thermogravimetric analysis, or TGA. It is normally either called as TG or TGA, thermogravimetry or thermogravimetric analysis. Differential scanning calorimetry, or DSC. So what TGA does, it measures the mass changes due to decomposition, oxidation or loss of volatile components. Now what DSC, that is differential scanning calorimetry, does, it detects the heat flow associated with phase transition, melting and crystallization. Now differential thermal analysis, or DTA, what it does, it measures the temperature difference between the sample and the reference material. Now these three you must have been heard before also. Now the dynamic mechanical analysis is one which evaluates mechanical properties such as the stiffness and damping. Now thermomechanical analysis, TMA, that measures the dimensional changes like expansion or contraction. Now in this I have not included EGA, which is the evolved gas analysis, because when you are heating a sample, some gas also may evolve, like EGA, evolved gas analysis. But for analyzing this evolved gas, either you need to use a mass spectrometry or a IR spectrometry. So that actually it is evolving and it is attached to the system, either a mass spectrometer or a IR spectrometer, to analyze the what are the gases evolved. So that is a different one. So therefore I have not included here. But yes, all the instruments are normally associated with a EGA system, or evolved gas analysis system. Now thermal analysis is widely used in materials, since in material science, chemistry, pharmaceuticals and polymer research, for understanding the stability, composition and thermal behavior of materials. Now these are the list of various thermal analytical techniques with the symbol, and then what is the property measured. So TG is mass, derivative thermogravimetry is first derivative of mass change, DTA is the again differential temperature is measured. Now DSC, or differential scanning calorimeter, where you measure enthalpy change, whether it is endothermic or exothermic, like that. Then thermomechanical analysis, the mechanical properties are being focused. Dynamic mechanical analysis, so viscoelastic properties. The dynamic load thermomechanical analysis, so DLTMA, so mechanical properties. And that whatever evolved gas detection are there, evolved gas analysis is there. So either detection means only qualitatively you know what are the gases are evolving, and analysis means quantitatively the amount can be calculated. So now these are the various other techniques. You can have a look for your knowledge. And these are also continuing here. So there are a lot of various parameters can be focused and lot of various things can be done by thermal analysis. So while carrying out this measurement, the furnace atmosphere can either be static air or a continuous flow of gas. So these two gives different information. So an expert in thermal analysis can tell you what are the information you can if you are going into and see various examples, then you can find out these are the conditions and you can generate various information from this. Now inert condition means either nitrogen, and what it does, it will inhibit the oxidation, because if air is passing, then lot of oxygen is there, and at high temperature condition oxidation is getting enhanced. The rate of oxidation will get enhanced and your sample may oxidize. So and reducing condition, if you want, then you have to purge hydrogen. So these are the various conditions you can change. So what are the general thermodynamic relationships based on which you do this type of analysis is that the Gibbs-Helmholtz expression is there, where delta G0 equal to delta H minus T delta S, and you know that this is a very famous equation of thermodynamics, where G is the free energy of the system, H is the enthalpy of the system, S is the entropy of the system, and T is the temperature in kelvins. Now consider a general equation like this. So this equation, whether it is a spontaneous or non-spontaneous or it is in equilibrium, can be told by calculating is free energy change. So if it is a like spontaneous, then delta G, the free energy change will be negative. So in this equation you can see the free energy will be negative. If it is equilibrium, then it is delta G equal to 0, and it is not proceed if your delta G is found to be positive, calculated to be positive. So for the Gibbs-Helmholtz expression can give you an idea about the spontaneity of a chemical reaction. So thermal analysis involves the monitoring of spontaneous reaction. In case of thermal analysis, normally we monitor the spontaneous reactions. Now thermogravimetric, now let us just see the what is thermogravimetry or thermogravimetric analysis. Thermogravimetric analysis is the study of weight change of a specimen as a function of temperature or time. Now the temperature is increased at a constant rate for a known initial weight of the substance, and the changes in weights are recorded as a function of temperature at different time interval. So just go through it slowly, you will know what is it actually. And the technique is useful strictly for transformation involving the absorption or evolution of gases from a specimen consisting of a condensed wave. Now a plot of mass versus temperature, that is called as thermogravimetric curves or thermogram or TG curves, permits evaluation of thermal stability, rate of reaction, reaction processes, and sample composition. So now measurements of changes in sample mass with temperature are made using a thermobalance. The balance should be in a suitable enclosed system so that atmosphere can be controlled. So now here the sample amount normally we take are in few milligrams. Let's say 2 milligram, 3 milligram, 5 milligram, like it is few milligrams. So you need to use a very precise balance where you can measure correctly a milligram quantity of sample, first one, and then wherever there is a balance which will be measuring the loss in your sample weight should be in an environment which will not be getting affected by the temperature change, or there should not be any airflow inside. So you have to take it carefully, because with small changes also this type of milligram quantity can you can misread the weight. So you have to take it very carefully. Now the temperature induced transition, what are the several physico-chemical phenomena can occur with increase in temperature, like dehydration can occur, decomposition, oxidation or reduction, phase change, etc. Now TG is concerned only about the temperature induced process which lead to change in mass. So in case of TG, we are not looking into any other thing, but during this procedure, if there is a change in mass, then only you can monitor in case of your TG. It will not tell about phase change and all. So weight gain process, what are the weight gain process? Are the absorption or oxidation? Because oxidation, if oxide are forming from a metal, then its weight will be increasing due to the incorporation of oxygen. And weight loss processes are what? Dehydration, decomposition, evaporation, desorption, etc. So now these are the typical few thermogram diagram which show variation of mass with temperature. Now you can show this is the weight percent and this is the temperature with temperature. Now these are the three different compound A, B and C. So you can see how it is going, the weight are changing with increasing temperature. Now you can just have a look. I have given here like 1, 2, 3, 4, 5, 6 and 7. There are 7 cases with what type of thermogram you are getting. So this is the mass and this is the temperature. Now at a first look, what can you get an inference from the sample? Say 1. In case of 1, the sample is thermally stable in the scan temperature range because there is no mass changes there or no mass loss is there. So in case of second, you can see there is a rapid initial mass loss is characteristic of desorption or drying. So there will be any water molecule has gone when there is initial temperature change. So it has been volatile. The water has been volatile and then it is stable. Now third case is single stage decomposition. Fourth step is multi-stage decomposition with relatively stable intermediates. Because where relatively stable intermediates, then you can see now this is with increasing temperature for a long range, it is not changing at all. So we can tell it is a stable intermediates. Multi-stage decomposition with no stable intermediate products, the effect of heating rate must be considered. So in case now there is nothing like a plateau, so it is just slow decreasing. So now it is intermediates are there, but they are not thermally stable. So in this type of cases, now your heating rate will play an important role to get important informations. Now gain in mass, because this is the case where it may be oxidation or absorption of something with increasing temperature. So mostly it is oxidation. So gain in mass due to reaction with atmosphere, oxidation of metals. Now in case of 7, now oxidation products are forming and then with further increase they are getting decomposed. So these are the type of information you can get at a first sight of some type of thermograms. Now this is a particular a typical block diagram of thermogravimetric system where you can see this is the reference electrode, this is the reference electrode balance, like everything is labeled. Actually you can have a look into this. Now the three main components are balance, furnace, the heating device, and then temperature measurement and control, because you are taking the sample and weight loss and all will be known from a balance. So the balance is important. Now since you are heating the sample, so furnace is important, and then you have to measure the temperature because you want to know exactly what is the temperature. So you have to measure it and control it, the increase in temperature. This is it. That was the block diagram, and this is a typical instrument. Now let us see one by one all the part of the balance, which is an important part actually. The basic requirement of an automatic recording balance. So it should be automatic recording balance. So it includes accuracy, sensitivity, and reproducibility, and it is highly capable of. So now recording balances are of two types: null point and deflection type. The null point type of balance, which is more widely used, incorporates a sensing element which detects a deviation of the balance beam from its null position. So now when it is exactly balanced, this is the null position. Slight deflection from this, the null sensor will sense it, and then it can measure the weight. A sensor detects the deviation and triggers the restoring force to bring the balance beam back to the null position. So the restoring force is directly proportional to the mass change. So like this, the measurement is the, like when weight will be changed, so there will be weight change, and this is the restoring force. This restoring force is related to your mass change. So now in the balance, you can position your sample in different way. There are a pictorial depiction of how the sample can be oriented inside your inside the furnace with the balance. So this all depends on instrument to instrument and manufacturers to manufacturers. So it all has some advantages or disadvantages. But just I want to tell you how they are being done. Horizontal arrangement is there. Here you need to keep your samples. And now this is the furnace. Top loading, then it is suspended. Now it's the furnace housing and this suspended. There are three types again. So these are the various types of sample orientation with respect to the furnace. The suitable samples for thermogrammetry are solids that undergoes one of the two general type of reactions. Reactants, it can products and gas, a mass loss will be there. Gas plus reactant products, a mass gain will be there. Now the process occurring without change in mass, for example, melting up a sample obviously cannot be studied by TG. Melting up a sample or phase change cannot be studied by a TG. Now, the various factors affecting the TG curve is the instrumental factor and sample characteristic. Now, what is the instrumental factor? This furnace heating rate and furnace atmosphere. And for sample characteristic, weight of the sample and sample particle size. So, let us see bit elaborately these points. Now, for furnace heating rate, the temperature at which the compound or sample decompose depends upon the heating rate. When the heating rate is high, the decomposition temperature also is high. It is not like you will say some particular compound is decomposed at 250 degree. But when the heating rate, in case of thermogrammetry, it all depends on the heating rate. They are depending on your heating rate, it may not decompose up to 400 degree also. So that it very well depends on the heating rate. So when the heating rate is high, the decomposition temperature also is high. A heating rate of 3.5 degrees centigrade per minute is usually recommended for reliable and reproducible TGA. So after doing many heat and trial, it has been found out that 3.5 degrees centigrade per minute is usually recommended for reliable heating rate, as reliable heating rate. Furnace atmosphere. Now the atmosphere inside the furnace surrounding the sample has a profound effect on the decomposition temperature of the sample. A purge of nitrogen gas from a cylinder passes through the furnace, which provides an inert atmosphere. Now the sample, what are the various sample characteristics? Weight of the sample. A small weight of the sample is recommended. Using a small weight eliminates the existence of temperature gradient throughout the sample. Because if you are taking large amount of sample and the furnace is placed, then just above we have seen how the sample is placed in a small crucible. And then this the furnace. So when you are heating the furnace, if sample is in a big quantity, then the inside it will not get heat properly. So they will be exposed to different heat than the outside sample. So therefore, you should take a small sample quantity. Particle size of the sample is that the particle size of the sample should be small and uniform. The use of large particle or crystal may result in apparent very rapid weight loss during heating. So now what are the applications of TGA? Let us see that. From TGA, we can determine the purity and thermal stability of both primary and secondary standards. Determination of the composition of complex mixture and decomposition of complex. For studying the sublimation behavior of various substances. TGA is used to study the kinetics of the reaction rate constant, and therefore the finding out the reaction rate constant. Used in the study of catalysts. The change in the chemical state of the catalyst may be studied by TGA technique like zinc chromate. Zinc chromate is used as a catalyst in the synthesis of methanol. So if there is some change during this use, can be find out from TGA. So now again continuing that, the thermal stability of material, oxidative stability of material, composition of multi-component system, decomposition temperature and kinetics, estimated lifetime of product, moisture and volatile content in the material, all can be calculated from TGA studies. Now optimum condition is, again to repeat it, it is a few milligram of samples, like 1 to 5 milligram is sufficient. Thin layer of samples or open sample container is there. And then because open sample container is required, because if something is going to loss, then there should be an outlet for volatilization of that. So inert gas flow and slow heating rate is recommended. This is a typical thermogravimetric thermogram of calcium oxalate decomposition. You can have a look to it. So you can calculate. See, for this calcium oxalate, there is various like first when you are going up to up to around 100 degrees, then it is stable, then there is a loss, then again it is stable up to say 4 or 500 degrees, then there is again a loss, then again it is stable for 100 degrees around 500 degrees centigrade, then again there is a heavy loss, and then finally this. So the final product may be of calcium oxide in all these cases, those are formed. So you can calculate from this how much like weight percent loss is there. You can calculate the what is being getting lost. Okay. The same thermogravimetry of calcium oxalate is being with the different DTG, like differential thermogravimetry data. This is the DTG data, which if there are small variations are there, then you can find a proper resolution with DTG, differential thermogravimetry. See, now this peak position is corresponding to this slope. So you can DTG will give a better resolution for the small changes which normally from TG curve or thermogravimetry curve you cannot find out, but in DTG, differential thermogravimetry, you can find out. And you all know that for a DTG, normally you get peak shape curve. So this is the finally it is the calcium oxide is the final product, and you see now the CO2 is forming, CO is forming, or H2O vapor is forming. All these things can be known from the evolved gas analysis either by IR or by mass spectrometry. So therefore we can tell that okay, these things are the thing which is being evolved from that also, and the corroboration is also from the weight loss in the spectra if you calculate. Now, derivative thermogrametry, the same thing, whatever I have told. If a thermogram is there, you can superimpose a derivative thermogrametry, because from the same by calculation delta mass, like change in mass versus temperature, will give a derivative thermogram. So both you can superimpose and then see if there are small changes, then that cannot be find out from normal thermogrametry, and that can be found out from the differential thermogrametry. So now DTA, what is differential thermal analysis? The technique involves the measurement of the temperature difference between the sample. Now up to this either TG or differential thermogrametry, where there is a mass loss or mass gain. But in case of DTA, this is the differential thermal analysis. So this is the temperature difference between a reference and a sample is being studied. So the technique involves the measurement of the temperature difference between the sample and a thermally inert reference material when both are subjected to identical thermal regime, heated or cooled at a constant rate. Now DTA techniques response to enthalpy change for almost all reactions irrespective of whether they are accompanied by mass change or not. So the material under study and an inert reference material whose temperature normally does not change with change in your is taken as a reference material are made to undergo identical thermocycles. Any temperature difference between the sample and the reference is recorded. In the technique, in this technique, the heat flow to the sample and the reference remain the same rather than the temperature. So now the heat you are flowing will be remain same for the reference and for your sample. Now with a particular temperature, whatever you have given, what is the temperature change in your reference with your sample is measured here, and from which you can calculate your data. You can have a look here. This is the differential temperature is then plotted against time or against the temperature. So DTA curve or thermogram. Now you can see it is a melting peak. It will get giving a dip, and this sometimes the exothermic reactions are like a positive change, and endothermic reactions and negative change will be there. So peak orientation either up or down in DTA thermogram depends on the instrument manufacturer. So it is totally of instrument manufacturer. So that whether it is exothermic or endothermic, it may be different in different instruments. Now the phenomena causing changes, what can be the different physical or chemical phenomena which can cause the change in heat or temperature, as some physical parameters may be adsorption, disruption, or change in crystal structure, crystallization, melting, vaporization or sublimation. And a chemical change can be of oxidation, reduction, breakdown reaction, chemisubstitution or solid state reaction. So these can be the types of reaction, though it is not limited to this list, there can be many others also, but just for typical some few common things I have listed here. This is a type of typical instrument block diagram. So here the reference is there. This is the reference and this is the sample. So equal crucibles with equal amount of samples. This is the furnace. Then the reference sample. Then this is the thermocouple to measure the change in your temperature between your sample and the reference. So this is the typical instrument. This is the block diagram. This is the block diagram where this is the exact instrument. And this is a typical DTA curve. So DTA curve is a plot of how it is plotted. DTA curve is a plot of differential temperature, means T sample minus T reference against the time or temperature. In the absence of any reaction in the sample, so there is delta T will be 0. So that constitutes the baseline signal. During an endothermic reaction, the sample absorbs it from the surrounding. So the differential temperature delta T becomes negative and attains a minimum value dictated by the rate of the transformation, heat transfer characteristic of the specimen holder assembly and its content to and the type of temperature sensors. So with all this, it depends. Now, what are the various reference materials used? Are the magnesium oxide, aluminum oxide, or silicon carbide are the various typical reference materials, inert materials which are used. And characteristic of the reference material used in DTA should be, they should not undergo thermal events before events over the operating temperature. It should be inert towards sample holder or thermocouple. Thermal conductivity and heat capacity should be similar to that of your sample. So depending on that, you can choose any one of these reference materials. So now DTA peaks are proportional to the total heat of reaction, which is equivalent to weight of the sample. So it can be for quantitative analysis. You can, for examples are analysis of polymers, ceramics and metal industry, phase transition, for example, sulfur. You know that sulfur undergo a phase transition, which is associated with some exothermic or endothermic parameters. So that all can be studied by DTA. Now see, this is a typical example of calcium oxalate and DTA curve. And the heating rate is 8 degrees per centigrade in presence of oxygen. So finally, this calcium oxide is getting formed. And this is the endothermic reaction, this is the exothermic reaction, again this is the endothermic reaction. So around 200 degrees centigrade, this reaction is occurring. Around 800 degrees centigrade, this is the reaction. So now in air, it is like this. And in nitrogen atmosphere, above process is endothermic. So now depending on the atmosphere, whether it is air or nitrogen, the process can be different. So all these things in combination for a given sample you can do. This is a known system, calcium oxalate. But sometimes you need to analyze for unknown system. That time you have to do all these things. You have to process it through inert atmosphere, you have to process it through oxygen atmosphere, through air and everything. And then you have to finally compare all the results to get a particular inference. Another example is copper sulfate. Now the DTA curves of copper sulfate, 3 endotherms are there. So copper sulfate 5 water becomes first 2 water losses, then 1 water losses again, then single water loss again. So this is the DTA curve where 3 endothermic peaks are there. So now TG and DTA, if you compare, then change in mass of sample. Now measure the temperature, like first TGA and then DTA. I'll be telling the see in case of TGA, change in mass of the sample versus here in DTA, the measure the temperature difference between the samples. Now here plot of a graph of change in mass versus temperature, whereas in this case the plot is graph of delta T versus temperature. Now change in mass gives information about change in sample composition, change in thermal stability, change in kinetic parameter, whereas here it is maxima and minima gives information about the exothermic or endothermic process associated with the sample. So these are the two types of, for a unknown sample you have to do in combination, like you have to do TG also, you have to DTA also for its total characterization purpose. Again, DSC, differential scanning calorimetry, like DSC is that this one. Here, the DSC measures differential heat flow associated with the transition in substance and reference materials linearly heated at a predetermined rate as a function of time and sample temperature in a controlled atmosphere. Everything is in a controlled atmosphere so that you can find out some inference. Now, these measurements provide quantitative as well as qualitative information about physical and chemical changes that involve endothermic and exothermic or change in heat capacity also can be monitored. Now, DTA is suited for determination of characteristic temperature, while DSC is additionally allowed for the determination of calorific values such as the heat of fusion or heat of precipitation, heat of reaction, like that. So this is the plot. Here it is dq by dt versus temperature. So this is the DSC. Now DSC and DTA, both DSC and DTA sample and reference both are heated or cooled at constant temperature linearly at predetermined rate. Now during a thermal event in the sample, the system will transfer heat to or from the sample pan to maintain the same temperature in reference and a sample pan. There are two basic types of DSC instruments, power compensation DSC and heat flux DSC. Both differ fundamentally in their instrumentation only, but finally with the data or with the inference, whatever they give, the result are similar. So this is a typical DTA machine where this is chrome. Now you can have a look with chromel disc. Chromel is nothing but chromium and nickel and chromium plus 9 other elements are there. So it is chromel. Now similarly, alumel is there, which contains nickel, manganese, aluminium, silicon, and 9 other elements. So chromel is positive wear, alumel is the negative wear. Chromel and alumel are registered trademark of actually a company which makes the DSC instruments. It is not very commonly used, but this is a trademark of the company which is making this DSC instruments. So this is a typical DSC curve of polyethylene terephthalate or PET. You know, PET bottles are present, so it is a typical DSC curve. Now, the last one is the thermometric titrations. So, thermometric titration is defined as titration in which endpoint is determined by measuring the heat generated during chemical reactions. So, during our first class, we have seen there are various types of titration. We have seen like acid-base titration, complexometric titration, precipitation titration, and then 2 or 3 more like potentiometric titration and all. So here it is another type is thermometric titration, not very common, but still it gives very important informations. Now principle of thermometric titration is that in this titration, titrant is added at a known constant rate to a titrant until the completion of the reaction is indicated by change in temperature. So here it is very important that titrant is added at a known constant rate, because you cannot change the rate. For other titration, the rate can be in between we can change at various rate. Finally, it is a visual detection of the endpoint. But here it is a temperature change, and therefore the constant rate maintenance is very important. So until the completion of the reaction is indicated by change in temperature. The endpoint is determined by an inflation in the curve generated by the output of a temperature measuring device. So this is a typical system for which this type of reaction can happen, and you can do the titration. So at completion, the reaction procedure, a molar heat of reaction, which is shown as measurable temperature change delta T. In an ideal system where no losses or gain or heat due to environmental influence are involved, the progress of the reaction is observed as a constant increase or decrease of temperature, depending respectively on whether delta H reaction is negative, indicating an exothermic reaction, or positive, indicating an endothermic reaction. The typical setup for this thermometric titration assembly. And the application are like titration of same acid-base titration can be done by thermometric titrations also. You have to use the thermometric instrument setup to do all this type of titration. So all these sessions, say this is acid-base titration, this is acid-base titration, this strong acid strong base, weak acid strong base, and this is a complexometric titration. So all these titrations are actually can be also done by this thermometric titration, because during this reaction there are various temperature changes are involved. So these are the type of plots you can have in all this case. Similar type of plots you can have a look. It is all similar type of plots what we are getting that time. So it's the last. Any questions? There's still time is there. We can have we can discuss few questions.